we're taking a look at heat transfer, right? Heat can be transferred via conduction, convection, and radiation. Conduction is through a solid, convection fluid, which is a liquid and gas. Radiation is through a vacuum. Our focus today will really be on conduction, right? In order for heat to flow, there must be a temperature gradient, right? Temperature gradient means that over this distance x, there must be a change in temperature. Every temperature is here with the same, no heat will flow, right? Heat can only flow if there's a change in temperature, all right? So in order for heat to flow, let's say heat is being supplied by a particular power, right? So the power or the rate of heat flow, we call this rate of heat flow, right? Which is P. Rate of heat flow is dependent on a few things. Number one, which one do you think, well, anybody, in fact, before I tell you, what are some of the important things that would control how fast heat flows through there? Number one, temperature gradient, right? Change in temperature. So the difference between theta 1 and theta 2. What else? The material. So that's called the thermal conductivity. So every material has something called K, right? Every material has something called K, thermal conductivity. The higher K value, the better the conductor. Okay? Right? So the higher your K value, the better the conductor. Nice. What else? So it's dependent on K directly or inversely. The higher K is, the faster it will flow, right? So directly. What else? You think the longer it is, the faster it will flow? No. But the longer it is, it will affect it, right? So it's inversely related to X. That's okay. Anything else? Anything else that's important? We have K, we have the length, we have the temperature change. What else? Look at it. No, what controls the heat flowing through this? So we're focusing on this. So we said length controls it, right? We said temperature change, right? This length here could also be thickness, right? Right? It could also be the thickness of the material. One more thing. Look at the dimensions of this. Our area. Area, right? So directly related to area. So basically the rate of heat flow is dependent on this, right? And because technically the substance loses heat, you would always see sometimes that it include a negative sign. All right? Because the heat being lost as it transfers through the material. Okay with that? So the rate of heat flow is dependent on the cross-sectional area, thickness of the material, the temperature change, and the thermal conductivity. Everybody okay with that? So these are the quantities that affect the thermal, the rate of heat flow. Please remember that P is the rate of heat flow, right? Which is equal to energy over time. Right? One little thing I want to remember. Yeah, Diane? You okay there? So Diane, suppose see this quantity here. This quantity here is what we call the temperature gradient. You get through the what we put them? Yeah. Right? It's called temperature gradient. So instead of writing it like that, sometimes we write it like this. Change in temperature over the thickness. So they might give you a length here and a length here, and you have to minus, right? So you get a thickness. This is called the temperature gradient, right? So Daria, do you think the temperature gradient is directly proportional to the rate of heat flow? So in other words, if you have a high temperature gradient, will the heat flow faster through it? Yeah, yeah, right? So if here's 10 degrees and here's 1 degree, as opposed to 10 degrees and let's say 0 degrees, right? The higher the temperature gradient, the faster the heat should go through. That's okay, right? But one of the things that we need before we start to practice using this, we need to understand how temperature gradient and K related, right? We need to understand how these two things related. So for example, if I give you a good conductor, what the temperature gradient will look like. If I give you a poor conductor, what the temperature gradient will look like. Okay. Right, so we're trying to develop now some kind of relationship between right? We're trying to develop a relationship between K, thermal conductivity, and temperature gradient. Anybody can see how they might be related? Huh? Yeah, they're inversely related. What shall we got up, right? Let's say, right? So let's say that P is a constant, the power or the rate of heat flow through the substance is always going to be P constant. A is a constant, and we want to develop a relationship between these two people here. That's the same formula, right? You'll see that? So these two are constant values, right? Let's see if we can make temperature gradient the subject of the formula. What you'll get? You will get P divided by A on K. That's okay? Yeah? Here. You might understand what that will pick up here, right? Let's focus on one thing. Right? So you'll recognize this. You will recognize that the temperature gradient is proportional to 1 on K. Right? We are assuming that these two things are constant. So it's not going to affect anything. So what we see in here is that they're inversely related. So we're seeing that they are inversely related. Right? So inversely related simply means this. It means that a good conductor, right? Good conductor has a low temperature gradient. And a poor conductor has a high temperature gradient. Right? We'll take a look at the graph, right? And we want to see if this makes sense, right? We want to see if it actually, why would a good conductor have a low temperature gradient, while a poor conductor have a high temperature gradient, right? Because in a good conductor, any heat just flying through, right? Just going through extremely fast. But why the temperature gradient low? All right, so we're gonna take a look at that here. We're gonna take a look at why. Right, but before we do that, let's see if we could represent this graphically. All right. Taking this off, right? Again, it's in your handout, but you all come in person for a reason, right? I like to watch on the board and follow and fit. Watch on the board and pay attention. We'll start here. All right. So let's see if we can represent this graphical. All right. So on one graph, I'm going to draw a poor conductor and a good conductor. But you have to tell me which is which. All right, Soraya? So let us go with temperature here and thickness here. Right? So I'm going to draw two graphs. Right? So both of them starting at theta 1. One graph looking like this. And the next graph finished looking like this. Right? This is theta 2. Right? We have two materials. K2 is more than K1. K2, better conductor. Good. Bad. Right? So question, which graph do you think, right? Which line do you think belongs to K2 and which one belongs to K1, right? And I'll pick on the one that passage you see in here. Right? I'll put that here right through. Yeah. Lamin Yamal. Tell me something there. Which one I think is K1 or which one I think is K2? K-Lin. Watch this way. Yeah. Which one? Which one is K1? Which one is K2? I think this one here is. Just make a guess. Make a guess. Pick one that's around. What do you think, Jacob? Which one do you think is K1? Which one is K2? What you are seeing here? Good conductor, low gradient. Poor conductor, high gradient. So watch the graph and tell me what you think. Yeah, Jacob, sorry. Which one is the first line again? This one? This one? So you're saying that this one is K1 and this one K2? What y'all think? Yeah?
Opposite. Poor conductor has high gradient, right?
Right. Poor conductor. Let me use the word poor, right? Sorry.
Right. So then the gradient of theta one.
Okay, by the way, which gradient larger? Line 1 or line?
Theta two. Now bigger gradient than this.
No, so which one has the bigger slope? So if you had to slide down one of these lines, which one you will slide down fastest?
Theta two.
This one.
That one, yeah.
Right. So
That's
K.
K1. That's really K1 is good.
So K2 is the better conductor, the poorer conductor. No, I'm saying it wrong, you know, I just asked him. K2 is the better conductor, and so the better conductor should have the higher gradient or the smaller gradient. Right? The better conductor should have the smaller gradient.
Right, then K1, right?
Okay.
Is really
Right. Very good. Right? So this is the smaller slope. You're seeing that? This slope is smaller than this slope. This gradient is smaller than this gradient. So the smaller gradient should have the good conductor. The larger gradient should have the smaller conductor. Right? Please remember, this is no slope, slope, even more slope. All the slope in the world. All right? So please remember that gradient increases from here to here. Okay? No gradient, all the gradient. All right? So the way to remember and understand slope is like sliding down. Like pretend both are slide, whichever one you would slide down the fastest as the higher gradient. Okay? So the better conductor there is K2 and the graph for it will look like that. Are you okay with that? How about yeah. Right? Question. Yeah, forget question. Anyway, right? So pay attention to the graph. You'll notice that the graph starts at the initial temperature, finishes at the final temperature. Do just draw a random line, right? Make sure it starts and finishes at the particular temperature. Right. Question. Do you think in real life you're gonna be getting straight? Well, I shouldn't say in real life, ideally. Ideally, you'll get straight lines, but really and truly, these things are curved. But you want it to be a straight line. So the way to get it, for example, if I give you a metal and you want the heat flow in here or the temperature going to be a nice straight line, what you just do is just insulate it. It's called lagging. Right? So what you have there is something called lagging, just insulation. Right? So by lagging it, you're allowing the heat, you're allowing no heat to be lost to the environment. Okay, so a lagged, right? A lagged material will give you a straight line. Unlagged will give you a curve. That's okay? So we assuming most of our materials are lagged or perfectly insulated. Okay? Get out again? Do it, myself. All right, so just make a note of that. Perfectly insulated, right? You'll end up with those straight lines there, right? Why not? The first is the first organic. Okay, you see that? All right, so a black wood stove with surface area 4.6 meters squared. It's made from cast iron of a particular thickness. What does it? Right, only part one to begin with. Right, so a black wood stove with a total surface area of 4.6 meters squared. So for those who are not seeing that, write down the important thing, right? Surface area 4.6 meters squared. Cast iron. They give you the thickness of the cast iron. That is 4 by 10 to the minus 3 meters. Right, they give it K at the bottom here. Right, they said that K is equal to 80.4 watts per meter per Kelvin, right? That's the SI unit K. And then they said the interior of the wall is 650, while the external is 645. Temperature, ignore the temperature surrounding air, right? We don't need that one. Okay. That's the later one. Find the rate of heat conduction through the stone wall. Right? Once they use the rate, you know the formula to use, right? Yeah. Sorry?
So on this side, when you have this side space, right?
Yeah, when I read
It
it.
had a minus, but this side. It doesn't have a
No, the minus is just to show him being lost. So you don't have to write the minus all the time. Right? Okay, yeah, very much. Right, but that's something that I'll say to do it. Right, so find the rate of heat flow there. They basically give you all the quantities. They give you K at the bottom, they give you E at it. You have to figure out what the temperature change is, right? Oh, I forgot to ask you a question. Why the graph shape like that? I know you're working, right? But why you think it is that good conductor has a low temperature gradient, while a poor conductor has a high temperature gradient? I know we were able to show it from the formula, but why? Huh? Because it's lag now. Lag is just making sure that nothing being lost to the environment.
Like what? Question?
The question is why it is a good conductor has a low temperature gradient.
Because and this says how the bigger the gradient, the more gradient, lower
The bigger the gradient, the
more the same topics.
yeah, you're getting closer.
So
Getting closer. Right, yeah, sorry. Yeah, so going back to this one, then I'll come back here and explain that, right? Watch this here. So when you plug in it, remember the same formula, remember the minus sign just indicates power loss, right? When they ask the magnitude, it's not important. So you plug in your K value, you plug in your A, and you plug in your temperature change, right? That's the final temperature, and that's the thickness, right? How much is this?
It's 2.77 times 25.
Okay. Two. Does that? Huh? What's that? Yeah, it was. Sure. Yeah, it's what? Right? You okay with that? That's the SI unit, right? Is what? I just right. I did after. Right. So what you see? Why it is a good conductor has a large temperature gradient, right? So let's pretend, sorry, small. Let's pretend this is a, let's do both of them. Good conductor, bad conductor. Right? Good conductor has a small temperature gradient. The bad conductor has a large temperature gradient. What does temperature gradient mean again? Huh? Over a particular thickness, right? So let's say the thickness here is X. Thickness here is X. A small temperature gradient means temperatures close. So I'm just making up some temperatures. 30 and here is, let me say, 28. Right? Here is 30, here might be 10. Right? Why? So that's the main reason. This is a good conductor, right? So in a good conductor, the temperature change is not going to be that large because heat will flow through it easily. But in an insulator, the rate of heat flow will be small, right? So therefore, a temperature change here will be larger. Okay? So because of that, that's why these things happen. Okay? So you can explain it in a microscopic way, and you can also explain it macro with the formula. Right? All right? Everybody okay with that? Nice. Let's see now. So we understand that. Good. Let's say that I give you a material looking like this, and I ask you to find rate of heat flow. Right? And technically, most materials like this. Right? So for example, I want to get rate of heat flow through this wall. Right? This wall will be made up of concrete, cement on the outside, and probably red bricks on the inside and in the middle. So if I want to get a rate of heat flow through this wall or through the board, it's made up of different materials. Those materials are called that type of wall is called a composite wall, right? It's made up of more than one material. So for example, if I give you a wall like this, material 1, material 2. Let's say it's the same thickness to make it simple, right? But here's K1 and here's K2. Two different materials. K1 is more than K2. Let's say it's the same thing. Let's say the thickness here is 1 centimeter and the thickness here is 1 centimeter. Right? They both have the same area, and the temperature change here. Let's say we know those values. Let's say here is 30. Let's say here, just making up something. Here's 28 and here's 20. And heat flowing through it like that. Right? I want to find the rate of heat. Right? But remember, that's the formula I know. So I know E, I can find the overall temperature change and I can find the thickness. But what's the big problem here? Yeah, two different materials, two different K values. So what will make this easy, Saraya? What will make this easy? We have temperature change, we have thickness, and we have area. What will make it easy? If we have what? Same material, same K. Right? Same K value. So the problem is we need to get one K value. Right? Not the average. What we had to do is find the equivalent. Right? So we had to find the equivalent. Right. So here's where it get a little complicated. Right. So take a 10-second break here. Now 10 seconds. So we said that we want to get one K value, right? Online, you go with Michelle, Katrina. Yeah? All right. Okay. 10 seconds finish, right? So let's say you have this material and you have this material. This calculation will be simple if I could convert this to all calculator or this to all paper, right? So that will make it easy, right? So let us see in this example, K1 better than K2. So I want to get all K1. So I want to get only K1. Remember, K1 is the better conductor, right? Right? K1 is the better conductor. So I want to get K1 only. So if I take off K2, right? We don't know the value. Just answer this. If I take off K2, do I replace K2 with more K1 or less K1? Do I replace K2 with more K1 or less K1? So for example, do I put same K1, do I add more or do I add less?
Yeah, add more.
Sorry. Or do I add less?
When you add more,
Do I add more or less?
you add more to make up for the C2.
So would you add more to make up for the K2?
Yeah. You
Yeah.
add more.
So here's what Maki's saying, right? Maki's saying that K2 is a real bad conductor, right? Let's make up a time. Maki's saying that for heat will flow through here in 2 seconds, right? Okay, let's say 5 seconds, right? So therefore, heat had to flow through here in 5 seconds.
Yes.
So if K1 is a good conductor, if I need to put more. That makes sense?
Yes.
Are you sure? Soraya and logo in there. Soraya and logo in there. Right? So here's what I'm saying, right? Right? I'm going to make it a little bit easier, right?
Oh, yeah. Yes.
Right? So I'm just making up some time. It takes 1 second to flow through K1 and it taken right? And it taken 5 seconds to go to K2. K2 is a bad conductor. Right? So it will take longer, right? For heat to flow through it. Nice. So I need to replace K2 with K1 so that it will take 5 seconds. So therefore, I need more. If I put less, it will fly through. That will be too quick, right? I have to get the equivalent K2. You okay with that? And vice versa. If I wanted K2 only, then I would put less K2 on this side. So it will be smaller. You okay with that? Right. So it's just important to understand that you need more. Right? But what's important is the formula. There's a nice little relationship. I won't show you it now, but you can equate them and simplify. But there's a nice relationship that we could use. K1 on X1 is equal to K2 on X2. All right. This relationship allows you to find how much we're going to need of the unknown. Okay. So I want to show you how to use it, right? Head up composite walls. Kind of composite walls and just draw a small example here, right? Kind of composite walls and draw a small example. Right, so I'm using these same values here. I'm using these same values here, right? Ready? Come on, ready.
Already.
Yeah. But right up until here. Right up until here, so I can show you how to work it out. We're trying to get only K1, right? That's not answer, but that's. Ready?
Yeah.
So right, hurry up now, boy.
I don't. I don't.
Ready? Real simple, right? Ready? So here's what we need. Here's what we need, right? We ready? So we want to replace K2, right? So we want to replace K2 in this formula here, right? We want to replace K2, which is 1 centimeter, right? And we know that K2 is 10. And we want to replace it with K1, okay? And K1 is 40. So you want to know how much is needed. Are you okay with that? So I want to replace this, and I want to know how much X is equivalent to this. And X is for the K2, sorry, K1. So cross multiply, you'll get 10x is equal to 40. X is equal to 4 centimeters. That's okay? So what that means is if I want K1 only, it will be the original 1 centimeter, right? That was the original, right? Plus now 4 centimeters. That's okay? So I replace more, right? I replace the poor conductor with more of the better conductor. So the total length now is 5 centimeters. Right? So you follow how to use the formula? Watch. This here is what this is what you want to replace. You want to replace the poor conductor, right? And this is what you want to replace with, right? That's okay? So you don't want this anymore. You don't want this anymore. You want to use this now. So this will help you find X. That's okay? But the reason I showed you that thing before is that sometimes you might substitute the wrong thing and end up with a smaller value. But you know that if you're replacing the poor conductor, you're supposed to get more. Right? So all that means is that you just put them in the wrong place. Right? Just put it around. All right? But basically, when using the formula, the one that you want to replace goes here. Right? And the one that you want to replace it with comes here. All right? So K1 only 5 centimeters. Suppose it is K2 only. Work out that for me. Work out K2 only. Should it be more than 5 or less? Go ahead. Yeah. Wait, that's enough for. Tell me now, do you can prepare some more votes? Yeah. We got you? Are you okay with us? Yeah? So, you want K2 only, so I want to get rid of K1. K1 is 40 over 1, and I want to replace it with 10 over x. Cross multiply, you'll get 40x is 10, x is equal to 10 over 40 or 0.25. Right? So the entire length here will be 1.25 centimeters. That's okay? That'll be the entire length using K2 only. Everybody okay with that? Yeah? All right. So I think I gave you enough information there. I gave you K, I gave you A, temperature change, and thickness. Find P for me. And number 2, find P. Take your time. You can choose wherever you want. Is that not covered? Yes, yes, it is. You could choose whatever you want, right? All in terms of 10 or all the way to 50. Anything you want. Right? You got the same one. Yeah. Well, yeah, you can do it, right? If you want to use all of the 10 or all of the 50, that's up to you. Anyone can do. So you could choose whichever one you want, right? Right? You could call here K1. So you could choose all K1 or all K2. Anything you want. Huh? How about? On that, huh? Their shoes are power. I just want the mark. I just want the word to power. What shall you use? All K1 or all K2? All K1,
I use all kids.
all K2. Right, so I'm going to use only K2. Right? Only K2, so it means I need to get rid of K1. K1 is 10 over 5. Oh, just one problem, right? All these questions should be done in meters, right? So convert to meters after. Right, so 10 on this, all K2, so getting rid of this. 50 over X. Cross multiply, you'll get X is equal to 250 over 10, which is 25. Anybody get that?
Yes.
25 centimeters. So now, the total thickness will be the 25 plus the 3. So the X value will be 25 plus 3, which is 28 centimeters. Okay, which is equal to 0.28 meters. Right? Everything must be done in meters, right? So as you all said, K is 50, area is 5, temperature change is 10. Temperature change is 10 and thickness is 0.28. Well, the overall is mine. You don't have to.
You'll get the same thing, right?
You'll get the magnitude of the power. How much is this? 8, 9. Huh? Right? So that is the rate of heat flow. Anybody use K1 only?
Which one do you got?
Anybody use K1 only? Go and use it now. Go and use it now.
Serious. Why?
Make sure we're getting the same one.
Yeah. Yeah. Yeah.
Right? Any questions online there? Tina, you got it? Kalina? Kalina, you okay? So the change in X is, yeah, 0.28. Adding 25 and 3. Right? All right, last question, are we done? Huh? You have more? Okay, no problem, we can say it more than once. You can definitely do more than one. Yeah.
Lalaki.
Yeah, relative siya, that part. I apologize, but I did best I could do me there. Huh? I'll take long, I put here and here. Pick a figure now. And zoom in. Take a little pick and zoom in. I see you down, Jamie. Okay. Please, Jamie. Try that in. Last one, yeah. Yeah, what are you doing now? Oh, yeah. Last one here. This one is a brick, boom, and brick, right? More than one material. Okay. But, go by recess. Number
And we did look at done.
Vou passar? Aí, ó, quer segurar. Já está de boa na vida before, that's it. Quase tudo material agora, Manila, sabe? Dai, não faz isso. Ah? Vai, a Bíblia, eu lembro com você. Não faz isso? Ah, tá, direto não, é? Finish não faz isso. Oh. We're not,
That's.
Well, the 6 Really no, because of it. So, of course, imagine that just currently here is one because with each zero. See, it is plus five. Good, good. It's minus yeah. I got one. I got one. I get 9.9. Those seem to be one pump. See, 0.4 by 35.1. Seriously, so I was very cool. Me too.
all right. Now for the moment of. Let me see how this works. So we know heat will flow this way. So I saw somebody had the graph upside down, right? The heat will flow from high to low. Okay. All right. So let's see how the graph will look. What are the thicknesses again? 10, 5, 10. Okay, so we just average in here. Right, that is 10, then half of 10, then the remainder. Right. So it might look something like this, right? It might look something like this, but you all see that color. Right, so this is the better conductor, poor conductor, right? Which is a better conductor than foam, right? Yeah. So the foam would have this sharper gradient. Right? While this wouldn't be so good, this wouldn't be so good. Try to make sure the gradients are the same, right? Here is brick, here is pool, here is brick. Right? Here is 30 degrees and here is -5. Okay, so the graph will look like that. Try to make sure that the gradients and the brick look the same, right? No, how to be a straight line? Can be a straight line. There's two different thermal conductivity. All right, so it will look something like that. Just try to make sure that the gradients of brick look like the same thing.
Yes.
Parts 2 now. Part 2, thermal conductivity of brick is 0.48 and foam is a thickness of brick that will have the same effect of 5 centimeters of foam. Right? So you want to replace the foam in a way with brick, right? So the foam was where's the foam? 0.016. And it had 5 centimeters, you said, yeah, 5. And I want to replace it with brick. Right? Cross multiply and solve x. You'll get 5 by 0.48 all over 0.016. Right? How much is that?
150.
150, 150. So does it make sense? More of the better conductor to replace it for conductor. So that makes sense, right? And then part 3 now is to put everything into the rate of energy formula. Here I'm using brick alone, so I'm using 0.48. Question said per meter square, so the area is 1. Temperature changes from 30 to -5. How much is that?
It's 30 plus 5.
Right, so it's 30 minus -5, right? So that will be 35. And what is the thickness now?
1.7.
Right, so you're adding 150 to 10 plus 10. That's 170, which is 1.7. Okay, because remember it's brick alone, right? 10, 10, and the 150 in the middle. Okay, but remember to work in centimeters. How much is that? 9.9. 9.9. Everybody hear that? Okay, so that you get thermal conductivity work, right? We'll look at radiation next. Wait, our class finishes right here Tuesday. No. Friday, I was on the. All right, online. All right, do one next.